In this lesson we will learn to conduct a transient stability analysis in Etap. So transient stability analysis is used to measure the tolerance of a power system to the disturbance, or how much disturbance a power system can withstand before becoming unstable. So Etap provides the ability to conduct these studies, and to understand more about transient stability, I suggest studying the single machine infinite bus system and the swing equations and equilibrium criteria. So you will get a better understanding about what results are we going to expect after conducting a transient stability analysis. So in Etap we can simulate various disturbances and thus observe the system stability, and that is whether the system will be stable or unstable after the disturbance. So let me make a new project over here. So let us make a two machine system which is connected by a transmission line. I have already drawn my single line diagram, and we have two generators over here. This will be the generator at which I will be conducting the transient stability study, and this will be in the voltage control mode, and this will be in the swing mode. So let us begin by rating all of these components over here, starting with this generator. So let this be a 10 megawatt generator which is rated at 11 kV, and this is already in the voltage control mode. So then I will go to the impedance and the model, put in typical data over here, and put a damping coefficient of 10. And then I will go to the inertia page over here. So this will be provided by your manufacturer, but all I know is that the total inertia is about 0.8. so in order to obtain the other values, I will start by putting values until this becomes 0.8 for my case. So this automatically updates the omega r square value, so which is a good thing, and all the other options, exciters, governors and PSS, harmonic, everything else I will put in default. So coming back to the capability curve, and I will now use the capability curve for my Q max limits, and I will be providing a power of 8 megawatts from these generators, and that's it. I will click on OK, and the other generator over here I will start to rate this also. So let me begin with this. This is put in voltage control mode. They are always put in voltage control mode in default. So let me change this to swing, then I will again rate this for 10 megawatts with 11 kV voltage, and again we will have to enter in these values over here. And click on OK. And for the transformer, this will be 110 to 11 kV with a 12.5 MVA, and the impedance will be the typical values, and click on OK. Similarly for here, and the transmission line, I will select the type of conductor from here, let me go to the T&D book and select some conductor. Okay, this is good for me, and I will select the same. And next, the configuration. So this will be at a height of 50 feet, which is put at random for with 3 feet each other. This updates the geometrical mean distance. Everything else I will put on default and click on OK. And this load will be 6 MVA with 0.85 power factor, and this will be again 7 MVA with 90% power factor, and click on OK. To verify everything is in proper order, we will go to the load flow analysis and conduct a load flow study. So everything is good. Now let me go over to the transient stability analysis mode over here from my mode toolbar, selecting the transient stability analysis. In order to conduct a transient stability analysis study, we need to generate a disturbance on the system. So we need to create a disturbance on the system, and for creating that disturbance, I will go to the edit study case over here, go to the events over here, then I will go to add event, and this event will take place at time 1 second, and the action that takes place is that the device type is bus and the device ID is bus. So we can change this to generator, and we can make different types of actions over here, such as we can create loss of excitation, droop and so on. So I will put this on bus to make it simple, and we will simulate a 3-phase fault on t equal to 1 second, and creating another event at time t equal to 1.1 seconds. I will just clear this fault over here. So we have a disturbance now, and then I will go to the plot option over here, and I will plot the generator 1 and all the bus voltages. So I will have to check all of these, and I will click on OK. Then I will go to run the transient stability option over here, and now we have these values populated alongside my generator. So this 21.3 degree is the rotor angle of the generator, 1.843 per unit is the excitation of the generator, and the speed of the generator is shown in RPM. And these are the percentage voltages and the frequency over here. And this also brings the transient stability time slider. So I will select the action list from here. So I have this action list which shows me the time in seconds and the event which will take place. So after sliding this to 1 second, I have the event Q1 happening, that is the 3-phase fault. Then after 1.1 seconds, I have the fault being cleared by my event 2. So let's see. Previously the rotor angle was at 21.2 degrees, and post fault condition this is about 40.8 degrees. So this is oscillating about the previous value, that is 21.3. So in order to use this data graphically, we will go to the plot options over here. So select the generator 1 and the power angle relative. So I'll click on one of the options over here and click on OK. So this brings the generator relative power angle. So as shown before, the rotor angle was previously at some 23, and at 1 second the fault occurs. So the rotor angle now swings and this settles to the same value after a period of 5 seconds. So let us observe the bus voltage also. As you can see, for the bus voltage we have about 100% till 1 second, and the voltage reduces to 0 and again rises from here after 1.1 second. If we want to simulate the study for a longer period, we can go over here to the total simulation time and change this to 10 seconds or 15 seconds if I want to, and we can also change the simulation steps also and the plot time step also. So let me increase the simulation time and observe the graph now. So as you can see, the disturbance has caused the power oscillations for about 4 seconds after it has occurred. So at 1 till 5. And then we have the report generator over here. We can generate the complete reports from over here, such as the exciter, dynamic stability, complete report, action summary, and so on. So now we have seen a system which is stable. So going to this option over here and selecting the relative power angle, you see this system is stable system. So what happens for an unstable system, we will just see now. So I will turn off the damping over here. Damping coefficient is 0, and we will again run this transient stability analysis. So let us see the relative power angle now. So now the system is not stable even after 10 seconds. So this is not a stable system. And we will go back and correct this, and I want to show you some more plots. So in order to activate more plots, I will have to go to this option over here, and the generator option, generator 2 is to be checked, and I will click on OK and again run this calculations over here, and to the plot options. Then I will check the absolute power angle over here, and you see the absolute power angle is sync with each other. And let us see some more plots over here. Speed, current for the generator 1. So this is the generator speed. Generator speed increases and gradually reduces. And the generator terminal current, after the point of fault, the current increases sharply and oscillates and comes to the constant value over here. So this is how you run transient stability analysis in ETAP, and see you in the next lesson.